The thing about relations is that a lot of the illustrations that you see in textbooks have nothing to do with relations on interesting sets. And we have to be careful here because relation and relationship are words that get used in everyday life and have a variety of meanings. But in our context, in the context of computing or in sets, the definition of relation is very precise. And it's one of those things that's so simple you can hardly understand it, but it's not a fuzzy kind of deal. So, um, to get us started, way back in the 1970s, um, when the first graphical interfaces for computers became available, those were cathode ray tubes. They consumed a tremendous amount of power and were delicate and fragile and were only one color. And people with vision, that's kind of inner vision, not this kind of vision, were able to say, wait a second, we could do simulations of various kinds of things. And there was a game called Space Wars. This may have been the first video game ever invented. And I played it in 1972 or 1973. It was kind of a hard game because the controls were these little teeny switches that were all that were available on the PDP-1 computer that it was implemented on. But you could fly around in space, and the physics was accurate, and the dynamics were accurate, and you could get an idea. You could see what you were doing and develop strategies and so forth and so on. One of the funny things about Space Wars, and this continued into a lot of video games, but not necessarily all of them, is that you had a screen that you were looking at, and if you were moving along, so here's something moving along. If you hit the top of the screen, then you actually jumped back and came in at the bottom. And here's a situation where you have a path that does that 3 times. So and so you're moving along, and then you come out here, and then you're moving along, and then you come out here, and then you're moving along, and then you come out here. And the same thing would be horizontally. If you're moving along horizontally, this green path, that's one continuous path, as far as you could tell while you were doing it. So we don't have right now, as a class, as a species we do, any language for describing what's going on with that. And it's a little bit surprising if you read the book, which you should do because it has all the basic definitions. But if you read the book, it's a little bit surprising that what they're talking about in the book with these little toy sets with 4 elements or 6 elements or something has anything to do with this picture of the game Space Wars. By the way, I put a link to the, I'm not supposed to say this, I put a link to the Wikipedia article on Moodle. We're not supposed to use Wikipedia, but if it's useful, it's useful. Okay, so what kind of language are we going to have to describe a situation like this? And that's where relations come into play. So let's get a couple of basic definitions, and then we'll start to make things a little bit more interesting. So here we have a title, relations, and we have sets A and B, and we have their Cartesian product A cross B, and that is the set of ordered pairs little a, little b, where little a is in A and little b is in B. So these are definitions that are pretty standard. You get a couple of sets. That is the definition of Cartesian product. Even if you'd never seen it before, this is what you need to know. And that's a situation where something interesting might be happening. Now, a relation is a subset of A cross B. Any subset that you choose is a relation. Now that's much too abstract and broad to be of much use. So let me look at a couple of simple illustrations, but then we're going to start putting them to use, and that's where they'll come up computationally and in mathematics. And so here's a relation that is of interest, and I'm going to make this in the real numbers cross itself. So that's R cross R, or you might call that R2. So there's just a picture of near the origin of R2. And if I draw a curve, so here I've drawn a curve, and that curve, the points on that curve, are a subset of R2. That's a relation on R2. Now, based on what you might have been reading, nothing anywhere near this interesting might have occurred as far as relations in the toy sets that you're looking at. But this is an honest relation. This is something that people can work with. Basically, any graph of anything that you can think of is a relation. So so I can call this relation, I'll call it R for red, and this is the set of pairs XY, and I happen to know the exact equation here. I wrote it down someplace even. Once you start thinking of things this way, then you start to see these things everywhere. So this one, y squared, is x squared plus x cubed, and this branch of the curve continues. So there's an interesting relation, and I can write this as a relation as a subset. Well, I've done that. I've written an explicit subset of R cross R, and here's the test that an ordered pair has to satisfy in order to be part of that relation. So there's that. On the same set of axes, let me put another relation, and because any old subset would do, so I'm going to just take just a blotch, and I'm going to color it in green. And now I'm not going to have a formula, so G is a relation. So relations in R cross R are just graphs or blobs on the plane. You can get more exotic than that, but those are the ones that you'll run into the most. So in general, we can use that as a metaphor if we want to have a relation on two sets A cross B, and A can be something kind of silly. In big data, this is a very, very important thing, where A is the set of households and B is the set of Subarus or something, and so you have, this Subaru belongs to this household, that kind of thing, or this household has two Subarus. And any kind of time you have data that is associated with each other in some way, you can phrase that as a subset of the product of the two underlying sets, and you can do this way. So you imagine A is the horizontal axis. There may not be an order, but it's still kind of helpful to work things out. And so you can say, well, A is the horizontal axis, and you put an arbitrary order on the elements of A, and B is the vertical axis, and you put an arbitrary order on the elements of B, and then you'll have something. So let me illustrate this with one of the kinds of orders that you might bump into, and this order is represented by a graph. Now, I just said graph, and I meant something totally different. So this is a combinatorial graph as opposed to, say, a calculus graph. And a combinatorial graph has vertices and edges. So an edge goes between two vertices. So that has nothing to do with the graph of a parabola as you've seen it in algebra or calculus or something. So here is a here's some things. There's a graph, and the relation is that A is related to B if there's an upward line between them. So there are 6 elements here, and for reasons that might come up later, I'm giving these elements funny names. They are 12, 10. You'll see which one's which in a second. 6, 9, 5, and 3. So those are serial numbers. Those aren't, it's not like the distance from 3 to 5 is the same as the distance from 5 to 7. Those are just serial numbers. Those are the order that they got written down in a certain way that we will talk about. But so I have some points, and so I can think of the points of A as being laid out along the A axis, and this is also still in A cross A, so laid out around the B axis. And what we're saying here is that 3 is related to 5. So that would mean if I'm plotting the points 3, 6, 9, 12, and then 3, 6, 9, 12. A point in this is an edge in the graph. So I've got an edge from 3 to 5, so I have a point at 3, 5. So this encodes the relationship. So 3 is related to 5. I can't read them, sorry. 5 is related to 9. 5 is also related to 6, and so forth and so on. So anytime you have an edge, that says the bottom one is related to the top one. This is not necessarily a useful way to think about relations, and so the book talks about them, so we ought to, but in relations that come up in the real world, this is a you know what, this is a simple example, and this is already difficult to follow. So it represents a certain kind of relation on a set with 24 elements. And so we're saying these have labels, and we're saying the set with this label is, the point with this label is related to the point with this label, and so forth and so on. And part of the reason that these are very difficult is that here's another picture of the same relation. I think they have the same labels. I didn't quite check. And so this is, frankly speaking, this is a mess. You cannot use this to do anything useful. And this one only has 24. And if you have some kind of, so that would be a 24 by 24 grid on which we'd be putting the green points corresponding to the edges on here. And if you have any substantial amount of data at all, which you have to make it interesting, you're not going to be able to use these Hasse diagrams. That's the standard name for these things, and that's what the book uses. So let me just write down Hasse. So Hasse was a mathematician who thought these were fun, and actually was able to do useful stuff with them. I don't mean to be there. So that's what a relation is. To be useful, it has to be a relation on an interesting set. And that's why we're interested in them, not for the toy problems that you might be seeing in various textbooks. Okay. It's amazing to me that someone could publish this. And this is a much prettier picture. They're the same. That's already a problem with any kind of graph, combinatorial graph, is that how do you know when two of them are the same? We'll get into that. But for the moment, let's just leave that as a question. Okay. So a relation is a subset of the Cartesian product, and that's it. That's too broad to be useful. We got to be much more careful. So what does it mean to be careful about relations? And careful means understanding that some relations have some properties and some relations have other properties, and to know how to tell the difference. There are 3 basic properties that relations can have, and one of them has a negation. So here's the situation. A relation is reflexive. So this is a relation, I'll call it R, contained in A cross A. So it's reflective if the pair AA is relative to R. There's just it's like a mirror image. The other one's like a mirror image too, so people get confused about this. But reflexive means that anything where the 2 entries are the same is reflexive. So And remember, we're an A cross A. They're two. They can be the same because they've it's a strongly typed language, and they got the same type. If they have different types, then you've got different sets. So a set of ints is not a set of cars unless you start doing some exotic typecasting. But let's not get into that. Okay, so that's property number one, is being reflexive. Property number two is being symmetric. And I'm writing this off to the side because this is the one that its negation is also important. So symmetric means if AB is in the relation, then BA is in the relation. So there it is, expressed in logical terms with, now that's reasoning implication, not truth table implication. So you say, well, you know what, 3, 7 is in there. That means 7, 3 has to be in there. That's the property that they have. There is a property that I'll call 2 prime, which is being anti-symmetric. And anti-symmetric says that if AB is a pair in our relation and A is not equal to B, that those two together imply that BA is not in the relation. For symmetric, BA is in the relation. For anti-symmetric, BA is not. So those are clearly related things. They're talking about, if you have AB, do you have BA? And sometimes you do. Some relations you do. This would be for every pair. And some relations you don't have it for every pair. And so that's a distinction that you can draw. Certainly not every property has that situation. And the final of these 3 properties that relations might have is transitive. And transitive says, well, look, if I have AB is in our relation and BC is in our relation, that means that AC has to be in the relation. So those are the 3 properties: reflexive, symmetric or antisymmetric, and transitive. And those are the most important properties that a relation might have. And so let's illustrate that with a couple of things. First of all, if we go back to this relation here, we've got this one's antisymmetric. 5, 9 is in there, 9, 5 is not. I can't read these, sorry. 10, 12 is in there, 12, 10 is not. So this is an antisymmetric relation. All the relations that you have only go one way, because remember, we represented A is related to B if B is above A. So this is antisymmetric. The ultimate relation, the one that we're aiming at and we hardly ever achieve, is equality. And equality is a relation. So you've got 2 things, X and Y, and you ask if they're equal. Well, the ones where they're equal are in the relation. The ones where they're not equal are not. Equality has all 3. So it is reflexive, symmetric, and transitive. And this relation up above, the Hasse diagram above, has all 3. In the other form, it is reflexive, and it is antisymmetric, but it's still transitive. And the transitivity on that one is kind of straightforward, because what you have is 3 is related to 5 and 5 is related to 9, and this is implied transitivity. So 3 is related to 9. You can go up from 3 to 9. What's not related are 6 and 9. Those aren't related. But anyway, so you have transitivity by definition here. Equality is transitive. If this is going to sound stupid, if 3 is equal to 3 and 3 is equal to 3, then 3 is equal to 3. A better way to put that is if x is equal to 3 and 3 is equal to y, then x is equal to y. That's a much more interesting kind of situation. So these collections have names, and the name for a relation that has all three of the properties, not the anti-ones, reflexive, symmetric, and transitive, that's an equivalence relation. So equality is an equivalence relation. The one where it is reflexive, antisymmetric, and transitive, that's called a partial order. And not every relation has these properties. The equivalence relations are very important. We'll just have a whole lecture on those. And the partial orders are very important. Although I think at this point I might have said everything that needs to be said based on these Hasse diagrams. So let me finish up by going back to playing Space Wars with the little toggle switches on the front of the PDP-1 computer, which might have fit in the room where I'm sitting. I don't know. Anyway, the relation that we're seeing here, and we'll have to go into more detail about this, but this is one of the equivalence relations that we're talking about. We have defined an equivalence relation on the unit interval 0, 1 cross itself, and a lot of it is pretty straightforward, but then there is a change in the relation between what's happening between the horizontal sides and the vertical sides. So we're going to explore this more quickly. So the takeaway is that relations give us a way to talk about situations like this and many other situations. And so that's why we are going into this language. So those are important both in computing and in mathematics and in playing games. And so there's what they are.